Okay, the final chapter for the semester. Basically, solving an equation of any nonlinear equation, and we're going to see various iterative methods for doing so. Before I get into that, so if you look at Canvas on the main page, I put a practice final exam along with the solution, just like I did for the midterm. Go ahead and check it out. Keep in mind that the format's going to be very similar in that there's going to be several regular problems and then concept check questions, but it was a lightning round. The points will break down about evenly between the two types. Unlike the midterm, what I was supposed to do for the midterm, and we'll do in the final, is that graduate students have to answer more questions than undergrads. So, finally putting you in the hot seat. Okay. So, Thursday, next Tuesday, yes, we are having class on Tuesday before Thanksgiving, sorry. Administration frowns upon that being canceled. And then the Tuesday after Thanksgiving will be coverage of Chapter 10. And then Thursday after Thanksgiving, that's December 1st, will be, wait, is that right? No, December 2nd. December 2nd. So that's our last class meeting, and that will be a review for final. And then soon I'll have information about the exact time frame for final, like when it will be posted, when it will be due, and so forth. Okay, and one more time appearing at the Coast this Thursday. So for all of you Hattiesburgers, you can attend virtually, or I'll have a correct code sent for the meeting code for anyone who wants to still attend here. Okay. So here are topics that will appear on the finals, starting from the end of polynomial interpolation. This Burmeet was not on the midterm. All the differentiation integration stuff, and then what I'm about to cover starting today. Okay. So the problem that we're going to consider, very simple to state anyway. You're given a function f, then we just want to find a root of that function. And the function may have multiple roots, but the idea is really just to find a root. And throughout, I'm going to use the notation x star to refer to the root we're looking for, like the exact solution. All right. Now, for certain types of functions, you're able to do this using, for instance, algebraic techniques, tools like that. So here are examples of equations that you already know, or should already know, how to solve. Here we have a quadratic equation. You can try factoring or using quadratic formula. Here you can use your knowledge of trig functions at certain angles to get a solution of this, or to find or describe all possible solutions. But the set of equations, nonlinear equations that you are able to solve in such a manner is very limited. All I have to do, I can make a very small change to these equations to get new equations that you have no idea how to solve. So for example, if I put an e to the x on the right-hand side of a quadratic equation, or for this one, I just put a factor of x on the left side. So everything you've learned in your prior classes would not help you solve these equations. And the best we can do is try to get an approximation. So that's what we're going to do in various ways, is that we can have some idea of where a solution is. For example, maybe some sort of initial guess that might at least be in the ballpark, or maybe an interval that has a solution. Then that could serve as a helpful starting point. And then we could have some approach to getting closer and closer to the root. And we'll see various approaches from this chapter. But what they all have in common is that they'll be iterative in character. So you'll get some sequence of iterates Like you might have an initial guess x0, x1, x2, etc. And the idea is that these iterates, the sequence of iterates, hopefully will converge to some root x star. What we'll find is that there may be methods that are reliable, that they will eventually find a root, but they might do so slowly. Or there are methods that can find a root much more rapidly, but maybe they're not so reliable. It's not necessarily a clear winner in terms of finding, selecting a root finding method. Software that implements these methods might combine ideas from more than one to have software that people can depend on to find a root. Now, there are 4 methods in total that I'm going to show you. So just one of them today. But first we need to talk about some general concepts related to root finding that will be helpful in understanding all of the methods. So the first one is order of convergence. So how does, because this difference, xk minus x star, or xk plus 1 minus x star, that's an error after k or k plus 1 iterations. Obviously we want the error to go to 0. But in what way is the error going to 0? How rapidly is it going to 0? So order of convergence is a way of quantifying that speed of convergence. So if each error divided by the previous error raised to a power is converging to some constant as the iteration converges, then that power is the order of convergence. So for example, suppose r is equal to 1. That means that the ratio of errors converges. For example, maybe the error is being cut in half as the iteration converges. So the error is certainly going to 0. It's just going to take a while to get there. On the other hand, if the error is proportional to the previous error squared, then that means much more rapid convergence. So we want a higher power of r. That signifies more rapid convergence. Because suppose the error after a certain number of iterations is, let's say, 0.01. Then you have a cubically convergent method. So then that error next time around could be like 10 to the minus 6. And then you take another iteration, then you cube that again, 10 to the minus 18. So that would be an extremely rapidly convergent iteration. We're not going to see those in this chapter, but just to get an idea of how it doesn't take much a high order convergence to be very effective. Even quadratic convergence, which we will see in this chapter, means that you may only need to take 5 iterations or so, and then you're done. Because once the error gets to be around the order 10 to the minus 15, you can't really expect it to be more than that just because of the limits of IEEE double precision floating point arithmetic. So, because the machine precision, which is really the smallest relative error you can hope for, that's 10 to the minus 16. Okay, so in the case of linear convergence, this constant c has to be less than 1, because otherwise, if c was equal to, say, 2, for instance, that means that the error is increasing over one iteration to the next. So c has to be less than 1 in that case. But for orders of convergence greater than 1, that's not required. If r does not have to be an integer. So if r is between 1 and 2, then we say it's superlinear. Or if we can prove linear convergence, but the ratio is going to 0 instead of going to a fixed non-zero constant, that also is superlinear. And then if r is 2 is quadratic, or r equals 3 is cubic, and so on. This number c, the limit, that's called the asymptotic error constant. Certainly it's going to be non-negative. And finally, in the case of linear convergence only, there's a separate term, rate of convergence. Now, watch your terminology. Rate of convergence and order of convergence are not the same thing. So the definition of rate of convergence is given by this. So the way to interpret it is how many correct decimal digits you get in each iteration. So, as an example, suppose C turns out to be 0.1. So that means that the error is being reduced by a factor of 10 every iteration. So then you work out what this is. If C is equal to 10 to the minus 1, then you get rho equal to 1. That means you get one additional decimal digit of accuracy every iteration. So this is helpful in terms of describing how the error is behaving in terms of decimal digits. But what happens if R is greater than 1 is there is no fixed rate of convergence, because the number of digits you are gaining from one iteration to the next is actually increasing. And when we get to those methods, you'll see what I mean. All right. Just like for other problems, it's important to be aware of does a solution exist? Is a solution unique? In other words, is a problem well posed? Also, what about sensitivity? We saw that numerical differentiation was an ill-conditioned problem. Numerical integration is a well-conditioned problem. So what's going to happen in this case? So we do have an existence result from the intermediate value theorem that if you have an interval AB where the values of f at the endpoints are of opposite sign, and we're assuming all along that f is continuous. It's pretty difficult to do root finding with a discontinuous function. Then you know there's a root somewhere in the interval. And that's actually going to be the main idea for the first method that I'll show you, which is called bisection. Bisection is a method that you might have seen in a lower level class. I know it's covered in calculus textbooks, for instance. We can say a little bit about uniqueness. That if f has a root and the derivative of the root at the root is non-zero, derivative at the root, then there is a local uniqueness in that this. So for all y values that are near 0, this equation has a unique solution near this root. So in other words, the function is locally 1 to 1 if the derivative is non-zero. This next point is particularly important for numerical methods. Multiplicity of a root. So if f has a root at x star and the derivative is non-zero, we say that's a simple root. Otherwise, the function is degenerate. So we have a multiple root. So for example, depending on how many derivatives are equal to 0 at the root, we can call it double root, triple root. So for instance, if f and the derivative, first derivative, are 0 at the root, that's a double root. If f double prime is also 0, that's a triple root. This is bad for numerical methods, having multiple roots. So a method that would be very rapidly convergent, for example, quadratically convergent for a simple root, can end up degrading to linearly convergent for a double root. So as a simple example, x to the n has a root of multiplicity n at 0. For instance, I take n equal to x squared. So x squared is 0 at 0. Its derivative is 2x, which is also 0 at 0. But its second derivative is just a constant function 2. So it's just a double root. So functions that are flat at the root are a problem for numerical methods. And this takes me to the next point about sensitivity. Now, so the general definition I'd given way back in chapter 2 for the general problem of computing y equals f of x as an absolute condition number, which comes from a derivative. Now, this is not what we're computing here. Here we're trying to find a root. So if we're trying to find x star so that f of x star is 0, that's the same as saying this. X star is f inverse of 0. So you can think of x star as the output, 0 is the input, and f inverse is the algorithm that gets us the output. Now this is assuming that f is at least locally 1 to 1. So we're going to make that assumption just for convenience. So if we want to know whether this problem is well-conditioned or ill-conditioned, we could use this notion of a condition number being a derivative, but this is what we compute the derivative of to get that condition number. Now, it may have been a while since you've seen inverse functions. In fact, I've discovered that apparently, I'm not sure if inverse functions are even covered in our curriculum, like, at all. I remember at another institution, I taught about them in the calculus sequence, but I don't know where that's done here.
They're definitely covered in algebra.
Okay. Oh, like a 101 or something? Mm-hmm. Okay, that's something. Unfortunately, here we need to get into the calculus of them. So.
That I don't know.
Okay, well, that's why I'm covering it here. So I'm assuming that you guys don't know about inverse functions. Okay. So if f is a one-to-one function, what I mean by that is a normal function, to be a function at all, it has to pass what's called the vertical line test. That for each x, there can only be one y. If a function also passes the horizontal line test, so for each y there's only one x, then the function is 1 to 1. And that's when it has an inverse. So how you define the inverse function is y equals f of x is equivalent to x equals f inverse of y. So when you have these cancellation relationships, like f of f inverse of x is just x. And the other way, f inverse of f of x is x. And as a simple example, suppose this is your function, square root of x squared minus 1. So then, by solving for x as a function of y, I have this for its inverse. But you have to be careful about what is the domain of a function or the inverse. So you may have to restrict the domain for the inverse to be valid. For example, in this case, x has to be greater than or equal to 1 in absolute value for this function to be defined. Sure enough, we see from this formula that x is going to be greater or equal to 1 in absolute value from the square. Here we're choosing a positive square root to ensure uniqueness. So this function does not pass the horizontal line test unless we restrict ourselves to positive x. In this case, we have this inverse here. Now, what we care about is taking a derivative of an inverse function. So how do we do that? We can actually use this equation to get the derivative. Because what you can do is take the derivative of both sides of this equation with respect to x. So on the right side, you're just going to get 1. And then on the left side, you use a chain rule. So it's f prime of f inverse times the derivative of what's inside. So f inverse prime must be equal to 1. So then you can solve this equation, and here's the derivative of the inverse. So the derivative of the inverse is 1 over the derivative of f, evaluated at the appropriate point. Which makes sense because it's supposed to be your function as a line, y equals mx plus b. That's going to have an inverse. So the slope of that line would be 1 over m, because you're flipping rise and run. So in general, the derivative is reciprocal. So So what happens is the condition number for computing a root of a function f is 1 over the derivative. So in other words, if the function is very steep, so f prime is large, then the problem is well conditioned. Whereas if a function is flat near the root, so the derivative is small there, maybe even 0, then the problem is ill conditioned. Now, we can talk about this in terms of backward error. So I remind you what backward error analysis is. That the approximate solution, so we want to get x star, but suppose we get an approximate root that I'll call x hat. That is the exact solution of a nearby problem, meaning that x hat is not f inverse of 0, it's f inverse of some other y value that's near 0, that I'll call epsilon. So f of x star is 0, f of x hat is epsilon. So suppose that the derivative is small near the root, then what that means is, what is the derivative? It's a slope. So if the derivative is small, that means that the change in y is much smaller than the change in x. Well, the change in y is epsilon. The change in x is the difference between x hat and x star. So what that means is x hat could be the value of x hat could be the value of f inverse at a point that's near 0, but x hat is nowhere near the root. So I have some graphs that will illustrate what I mean for well-conditioned and ill-conditioned cases. Okay. So here on the left we have a well-conditioned case. So in both situations, here we have the exact root, and then here we have an approximate root. So we see what the error is. The error is the difference in x values. But then when you substitute that approximate root into a function, you get some nearby y value. And notice that in the well-conditioned case, epsilon is 0.235. In the ill-conditioned case, it's 0.25. In other words, the backward error, which is this epsilon, they're pretty close in the two pictures. But in the well-conditioned case, because the derivative is large, the change in y is much larger than the change in x. So the difference in x values is much less than the difference in y values, therefore the error is small. Whereas in the ill-conditioned case, notice that the graph of f is very flat near the root. What happens in this case is, so the derivative is small near the root, meaning that the change in y is much less than the change in x. So here's our backward error, but our forward error, the difference between these x values, is much larger. So, so the thing to keep in mind is, if you're generating a sequence of iterates that hopefully are getting closer to a root, you might decide when to stop iterating by plugging your iterates into the function and thinking, well, if f of x is getting small, then I can stop. The problem is that it could be misleading, because I could be plugging in some value over here into my function f, getting a small value, thinking, oh, I'm near the root, I can stop. But you're not actually near the root. Whereas over here, I could be picking, have a point that's really close to the root. I plug it into f to check if I should stop. And I get a value way up here, and I'm thinking, oh, I need to keep going. But actually, you already are really close. So, so it's important to pay attention to how your function is behaving as your iterates are converging. Is it very steep or is it flat? And you should consider using a different stopping criteria than just plugging your roots, your iterates into f and seeing if it's getting small. So unlike numerical differentiation and integration, and we can pretty much say that for ill condition or well condition just across the board, for root finding, it depends on f and how its derivative behaves as to whether it's ill condition or well condition. Questions about existence, uniqueness, sensitivity before I talk about any actual methods? Okay. So the simplest method we'll do today is bisection. So bisection rests on the intermediate value theorem. So the idea is we have some interval where we substitute the endpoints A and B into F, and we find if they have opposite signs. So we need that as a starting point. Because then the intermediate value theorem tells us that F has to equal 0 at some unknown point between A and B. So we have a starting point. So root's in there somewhere. What we like to do is narrow the search down. So what you do is you take the midpoint. That's where bisection comes from. We're bisecting the interval AB. So we compute the midpoint M, and then plug that into F. Now, if f of M happens to be 0, then of course we're done. We get lucky. But let's suppose we don't. Then, there are only two possibilities. Either f of A and f of M have opposite signs, so we search in the left half of the interval. Or, these two have opposite signs, so we search in the right half. One of those has to happen because f of A and f of B have opposite signs. F of M, therefore, must have the opposite sign of one of these. There's no other possibility. So we just cut the sides of the interval in half. So then we choose that half, and then we continue. So we'll take the midpoint of that subinterval, and so on, and it keeps getting closer and closer. So at some point, the size of the interval under consideration is so small that because we can actually say reliably that the maximum error is the width of that interval over 2. That there has to be a root, that the midpoint must be within that distance of a root. So, I'll show you the algorithm for bisection. Okay, and this example actually steps you through bisection for a specific function, so you can see that the values are getting closer and closer to a root. So here's the algorithm. So you have an interval at the start, where f of A and f of B have opposite signs. So what you do is you have this iteration going. So in whatever interval AB you're considering, go ahead and take a midpoint. You check if you can stop right away. So for example, if the size of the interval over 2 is less than your chosen error tolerance, then you can you might as well stop there because you know that you are within your chosen tolerance of the root. So that's a tolerance of the absolute error. So then the midpoint, because it's close to a root, you can stop and say x star is a midpoint. But if you're not there yet, then you go ahead and check on like if here's a way to check if f(a) and fm have opposite signs, you just multiply them. So you don't really care which is positive, which is negative, you just care that they have different signs. So that tells you what the new interval will be. So you'll set A or B equal to the midpoint. So now your new interval AB will be half the size, and that's what you use during the next iteration. So you'll keep going, and it's guaranteed that eventually the interval will get small enough so you know you can stop. Because it just keeps getting cut in half, 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 half. All right. Questions about the algorithm for bisection? So I mentioned that it's reliable, which is very nice to have. Not all methods have that property. But this is slow. The error is reduced by a factor of roughly 2, or at least it's reduced by a factor that's the ratio is at most 1/2. So you can save it as linear convergence, and the asymptotic error constant is 1/2. Now you don't. At this point, this is the first method we're looking at. You all don't have a frame of reference, but what I can tell you is that we can do better than this in terms of having a higher order of convergence, or even linear convergence with a smaller constant asymptotic error constant c. This is the slowest of the methods we're going to see in this chapter, but also the most reliable. So what you can do, and I actually had one of my students do this as part of their master's thesis, mixing methods, where after identifying interval AB, where there's a sign change, so you know what the root's in there, don't use bisection right away, but use a more rapidly convergent method like ones you'll see later. But if that faster method ever produces an iterate that goes outside the interval AB, you don't want that. You have to reject it, so then perform one iteration of bisection just to narrow things down a bit, and then try the faster method again. So that would be overall less work, fewer iterations to get to a root. So, like I said, it's good to combine ideas from methods for best results in terms of efficiency and reliability. I want to mention a theorem about the convergence behavior. This one right here. All right. So, if I define the iterate xk to be the midpoint of the interval AB from the kth iteration, then what you can conclude is that the error in xk, so the difference between that and the root, knowing the root is in the interval AB, is at most b minus a divided by 2 to the k. So here's why we can be certain that convergence is going to occur, because the numerator is fixed and the denominator keeps getting larger, so we can plainly see that the error is going to 0. One of the homework problems is to prove this theorem.
Which method can we use either of the methods to prove it, maybe algebraically or numerically?
Sorry, what?
Do we prove it using the definition, or do we prove it using the algebra, or do we prove it with the analysis?
Oh, I'm not particular about how it's proved as long as it's correct. Yeah.
Because the real analysis has exact same proofs, but only with definitions.
Oh, I see. Well, I mean, I guess there's not much in terms of definitions to use here, but okay. see using induction for something like this. So, but I think there's a reason why I did not say that in the problem. Okay, all right.
We'll assume it.
What?
We can assume it.
Yeah,
Whether it is induction or anything.
Yeah, okay. Yeah, because there are cases where I would want something proved a certain way, but not here. There's not a whole lot to prove in this case. Yeah, I have to keep in mind, this is not a real analysis class. Although what's kind of funny is, I've had students that will be taking this class and a real analysis class at the same time.
Oh, yeah.
And because they both have analysis in the title, people get them confused.
But they cannot be more different.
Yeah. That's actually the point. Yeah, because I have someone come to my office asking for help with real analysis. It's like, I'm totally not the person for this. And then they told my book, it's like, oh, got your class titles picked up.
It is confusing on Canvas though, because you'll just see like Canvas. It's always just usually your section number or a bunch of like fall 2021.
Yeah.
Math 260, and then just you see R maybe or N and nothing else.
Yeah. Oh, because it cuts it off. Yeah. Well, yeah, because in Canvas this class is such a long title because it's cross list and H01, D01 because I took all the Hattiesburg and Coast and graduate undergraduate sections and mushed them together. But yeah, they probably should rethink that.
I actually did that blunder. I sent a message on Canvas to Dr. Ding, and he was like, I don't teach 560. And I was like, what happens? Like, oh, I wrote the cross list 560 instead of 541 because they both had analysis in the end.
Oh, we're both cross listed and yeah.
Just kind of clicked it.
Yeah, I once got a evaluation at the end of the semester where the comment was about Dr. Ding. They put it under the wrong class.
How do you handle, like, what if it's a bad evaluation? Do you just like slide it under his door and be like, sorry, this was not for me?
I did not do that. The thing that's unfortunate is that, the instructor's numerical rating can be affected by that. And the thing is, like, we have a committee of faculty look at these and draw conclusions, and you just have to hope that a big deal's not made of it. So, yeah, it's interesting. Okay, actually, I want to check on which problems I assigned. Okay, 2, 3, and 5 in this section. So that means I did not assign this one, so I can talk about it. Because if the error is being cut by a factor of roughly 2 each iteration, and you're trying to get the error to be like run unit round off, like a relative error, then there's really no need to take more than like basically the precision number of iterations. Like the precision P of your floating point system, which in the case of IEEE double precision, P is 53. So if you take 50 odd iterations, then that's you can't really hope for more accuracy than that. But the thing is, that's a lot of iterations. Again, you don't have a frame of reference yet, but what I can tell you is that other methods that we'll see can achieve convergence in single-digit number of iterations. 50 is excessive. But at least you know it's going to work because you can try some of these other methods on certain problems, and after a few iterations, you can find that your iterates are diverging, and this is a pretty hopeless situation. So that's why this method is still worth discussing. Another drawback of bisection is that it is not the kind of method that generalizes to functions of several variables, because you don't, the existence result you get from the intermediate value theorem doesn't have a higher dimensional analog. Whereas other methods that we'll see, like this, actually pretty much all the methods that we'll see, fixed point iteration, Newton's method, CK method, all of them have some kind of generalization to functions of several variables. And whereas in this class, we're only dealing with a single equation, function of one variable. In the next course, in the spring, we'll see systems of nonlinear equations. So you have a function that maps Rn into Rn, and we want to find a point in Rn that makes a function equal to the zero vector. And some of these methods will be appropriately extended there. Alrighty. Actually, here's an example of bisection in action. So the function involved is this one. Not sure why there's so much space in the book. Thank LaTeX. X squared minus x minus 1. Now, this is a function that you can find the roots of using quadratic formula, but this is just as an example. So if I look at the interval from 1 to 2, you see that f has opposite signs. So there is a root somewhere between 1 and 2. And this polynomial is certainly continuous. So the intermediate value theorem will tell us there's a root somewhere in this interval. So what happens is, here's my starting interval. I choose the midpoint, plug that into a function, and see that it's negative, and that tells me what the next interval should be. So 1.5 and 2. So I keep this process going where I plug in the midpoint, and we see that as we plug in midpoints that are getting midpoints of smaller and smaller intervals, the values are getting smaller and smaller. They are going to 0, if slowly. And here are the midpoints. So you can think of these as the iterates that are intended to get closer and closer to the root. And we see that there is a convergence happening, again, slowly. Actually, the exact root is the golden ratio. This happens to be the example that I chose. So after 10 iterations, we're getting there. If we look at, this is the exact results at 10 decimal places. So we got at least the first 3 decimal places correct. So not that great, but so we could keep going just to get more accuracy. One of the homework problems from the very first homework, a MATLAB tutorial, used a function of mine called Newton's square root, and that used Newton's method to find square root of 2, and did a job in about 5 iterations. So that's an example that you've seen of a much more efficient method. Okay. Questions about either this or any homework problems? Got plenty of time.
The lights are turned on again.
Oh, yeah. Yeah, I don't understand that.
Probably if Alice is going bad.
I don't know if it's a question. Maybe asking you. You can just help get started on one, or any ideas, anyways.
I see 2 people have submitted quizzes during class.
Gotta call them out that way.
Of course, it also means that I'm looking at my phone during class.
If you take them down, Dave, you go down with them.
could ask for advice on 9.1.4.
914.
I just don't even really know where to begin.
Okay,
I stared at it for half an hour trying to think of where to
that sounds ominous.
begin. Hmm? That's another issue.
Okay. Okay, so here's the error formula that I'll show everybody in a moment. That is a general case where you're choosing any points to plug into f to approximate the derivative, but now we assume that the points are equally spaced. So what you do is, okay, so this is a formula that you're working with, but you're only concerned about the error, so we're just dealing with this. So what you need to do is take in the problem, you're given a formula for xi. So go ahead and plug that in here. And then try to simplify as much as you can. For example, any factors that do not depend on I, you can pull out of the product. But be careful algebraically. And actually, well, here's what I would suggest as a way to make sure you're doing it right. Instead of, so what you can do is instead of doing the general case right off the bat, I'll pick a specific case. For example, J and K both equal to 1. That's the center difference. Because in that case, it's known what the error is supposed to be. Where is it? Okay, here is the center difference formula. So this is what the error term should be.
Okay.
So if we consider that here, since j and k are both equal to 1, that means that n, which is equal to j plus k, n would be equal to 2. So you can see here we're going to get the third derivative. And the prefactorial. But then what happens when you plug in xi? So xi is equal to x naught plus or minus h. So if you work out what this is in that case, and you can see, oh, here's how it reduces to the error formula that I just showed you.
Okay.
Hold on. Here's a better example to use than that one.
Okay.
That's more interesting. Oh, this one right here. Yeah, use this.
Okay.
Because the numbers are more interesting. It'll be more illuminating as to how to get the general formula.
Okay.
And then, if you can see what to do from there, take a shot to general case and get an expression that would be in terms of j and k. And then try it on this case, which has j and k both equal to 2.
Okay.
And see if this, you get this free error term.
Okay. Right. Thank you.
Okay.
I was wondering that in this particular case, would the error term become independent of the x naught term?
Yeah, it does.
Because it cancels out.
Yes. And sure enough, that's what we see here. It is independent.
Exactly. Yeah. So it's not wrong if I get something like that. It's not incorrect if I go, if I end up with something like that. So.
That has that.
It's not dependent on x naught.
Yeah, in fact, it should not be dependent on.
Exactly.
Yeah, it'd be incorrect if it was.
That helps. Thank you.
Okay. Are there any problems that are turning out to be relatively diabolical?
It's probably just a me thing. I'm sure it was a fine problem.
Okay.
I'm still working on coding, I think 1.5, like 9.1.5.
915.
Yeah,
Oh.
changing it from Taylor.
Oh, I see. Okay. Okay. Right, so for a previous assignment, you would have done make Lagrange, as if you're using that. And yeah, okay. And since it's known, like, once you have Lagrange polynomials, how do you get the coefficients from them? Each Lagrange polynomial is derivative at x naught. So really in this case, what you're doing is you're doing a set of indices. So if I look at definition of make diff rule, the original one, where we have these indices from minus j to k. So in other words, you're evaluating the derivative at 0. Because you can think of this as a shorthand for these points, but instead of dealing with x naught plus IH for certain multiples I, then really you're just using the values of f at the integers to approximate the derivative at 0. And then, if you think of a linear mapping from the original points here to those points, the integers, that mapping would introduce this factor of 1 over h that's supposed to be there. Let's see if I mentioned that anywhere in here, but I don't think it did. Oh. Kind of. This is what I was referring to, the change of variable. And so you plug in x equals x naught, that corresponds to s equals 0. Other questions? So for, just as I mentioned in the 914, that you want to check the correctness of what you have by using various examples interspersed throughout the section, like these rules here. You definitely want to do the same thing in 915 for this part, where it spits out the constant in the error term. Of course, in the examples, the constant is a fraction. What you can do is use format rat. So whatever number your function returns for c, you can display it that way and more easily check the correctness. Because even I don't know off the top of my head what 1/30 is in decimal. I should know. I think it's 0.0333 or something.
Why should you know though?
Yeah. Good point. Yes, 0.0333.
It's time to stop.
I was just like, 5 fond memories is in 6th grade, I freaked out one of my classmates by counting in 12s. It was my favorite number. So. Yeah, doing it just as easily as a normal person would count in 10s. 12, 24, 26, 48, 60, 72, 84.
Yeah.
Okay.
Is there a reason for it that you'd like to explain or not really?
Like why it's my
The
favorite
personal, you said your favorite number is 12?
I don't know why.
Oh, okay.
There's a few different people that like the idea of a 12-base number system.
Really?
It's called Dewey Decimal.
Oh, okay. But I haven't heard that one.
Yeah,
That
it's
really
they like it because it's supposedly better for everyday use because it has so many factors.
Oh, okay.
Yeah.
Well, yeah, 12 is a very composite number.
It's what they use in the libraries.
Oh, okay.
Well, that's Dewey Decimal. That's
Oh,
how they
okay.
that's how they organize books. I said duodecimal.
Oh, yeah.
I've heard of
Do.
Where are
It's
you?
My bad.
Okay. Okay. Any other questions? I'll find virtual land too. Okay, so what about a better root finding method on Thursday?
How high can you count in 12s?